Good afternoon, class. I'm glad you're all here. Everybody seems to be present. I'm sure on your way here you saw signs. And there's a familiar sign that I'm sure you all saw along the way. It looks like this. Okay, what does it mean to you? All right, on the roads, you see this sign. What does it mean? Yes? Okay, maybe my drawing is not good. But it says, go on and then do a U-turn, right? It's a U-slot. It's the Fernando sign, isn't it?
Yes.
Okay. Now, what other signs have you come across on your way here that's limited to traffic signs? Yes?
The road intersections.
Come again?
The road intersections.
The road intersection. What is the signal for an intersection?
On the road, there was a cross mark.
All right, this one. And that's very mathematical. So when you say intersection, that's not a monopoly of language. That's also mathematical language, right? So our topic today has to do with mathematics as a language. I'll show you certain symbols and I'll find out whether you know what it means, right? Here's one. Can you tell me what it says? Oh, and this. Oh, yes. And this.
No parking.
Aha! And this.
Parking.
There's parking. So if this is parking, this means no parking. Nobody needs to tell you, all right? So that's it. How about this? I came from a religious school, and that's very often seen. Right? It means peace, pax. All right? So I come from Miriam, and I see that sign very often. Right? It's a symbol for peace. Let's have another one. Okay, this is from your statistics. What does it mean? Right, you're familiar with signs. Signs have to do with language. What do we need language for? Do you think you'll need something for language?
I think we need language to communicate.
Okay, another purpose of language. Yes?
Maybe we use language for common understanding.
Common understanding. When you want to do this, right? You want to send a message, right? All right. You see, that by itself is language. Nobody needs to tell you what I mean when I do that. It is texting, right? And there are other signs in math, because mathematics is a language. If I have something like this, what does it mean to you?
A is greater than B.
Now that's a sentence, right? That's a sentence. But sometimes if I have that, what does it mean to you?
It's the formula for.
There's formula for
the
the
circumference.
circumference of a circle. Okay, and this one,
Function.
it's a function rule. Y is a function of x. So some of these are mathematical. How does it? Do you say 8? Because there is an exclamation mark. But how do you read it in math? Yes,
8 factorial.
8 factorial. And in a longer phrase, what does 8 factorial mean to you? Yes?
8 times 7 times 6 times 4 times 3 times 2 times 1.
She knows how to count. Yes? Okay. Supposing now, I have this. Does it mean anything to you?
Yes.
So, what is the language conveyed by this? Somebody would like to try? This is getting more and more complex. How would you interpret this?
6 factorial.
Yes? Yes?
The quotient of 6 factorial minus 4 factorial over
2
When divided
factorial. How much is 2 factorial?
It's
2.
2. How much is 6 factorial?
720.
720, lovely. And how much is 4 factorial?
12.
24. So it simply means 720 minus 24 divided by 2. Now, this is what makes mathematics scary to people. But when you know the language, you feel confident, right?
Yes.
Now, if math is a language, then it must be used for conveying ideas. And ideas could be in words, could be in phrases, could be in sentences. Now, how does a deaf-mute communicate? Yes,
By a sign language.
sign language, like show me a sign language.
For example, like this.
What does that
I'm
mean?
sorry.
I'm sorry. I'm sorry. Okay. How do you say I love you? Yes? Is that it? I love you? That is the Laban sign? No. Right. See. Children would say. Right. So there you are. Language communicates ideas. And so if we look at language in that sense, mathematics is a language. It doesn't have to be scary. Because all it does is convey a meaning, right? And so, as we move on, we have, for example, these are symbols for relationships. Like this symbol, what does it mean?
Less than.
And this?
Equal.
And this?
Greater than.
So it could be any one of the three, right? Could it be more? No, there are only three relationships under the sun. Can we have them in combination? Maybe. If you put this and this, it becomes a letter Z. It could be greater than or less than. Then when I want to negate, I can have that. How do you call this?
Not less than.
Not less than. And this? And this?
Not greater.
Right. So that little thing there says not. And that's the reason why when you say this, okay, you say this. What does it mean? No parking. Some person told me, no parking is like that. Are you sure? Right. Think of your math. This is a positive slope, but you want a negative slope. So you say, right, next time you see a parking sign, see where it slants because it has some meaning. So now it's never too late to learn science. And that's what language is doing. We communicate, we become as one. But when the teacher uses language in a way that's not understood by the students, there's no communication. And that's where we fail in math. Okay? So now let's see. Let's go to more relationships. Let's have this. What does it mean? Yes?
M is parallel.
M is parallel to L. Read this sentence. Yes?
AB is perpendicular to CB.
Okay. And this, does it have and say anything? What does this symbol indicate to you? Yes.
Triangle ABC is a right triangle.
It's a right triangle with right angle at B.
Yes.
Right? Now, and this, oh my goodness. Right. What do you think it's saying? This is the time when students begin to fear math. There's so many crosses. Right. They're like being crucified. Okay, so let's expand what we got from here. The symbol that we got here, can we make use of it in this thing?
Yes.
Right. All right, how many lines do you have?
5.
5 lines. What are the relationships among those lines? Yes? Let's see. Angeline.
Line AC intersects line CD.
Yes. They intersect. What else?
Also, line BE intersects line AB.
And what kind of intersection is made? What's the relationship?
Line AC, line BE is perpendicular to line AC.
Okay. Is that right?
Yes.
And another relationship that you can get out of this. How about AD? Is it related in any way to another line?
Yes,
Yes, ma'am.
AD is perpendicular to CE.
Lovely, right? So you have all of those. There, now I have a different figure, right? What can you make out of this figure? What's the shape?
It's a kite.
It's a kite. Another word for kite. It's a parallelogram, yes. And what are the relationships? Yes, Fritz.
Segment AB is
AB
congruent to
is congruent
segment
to
BC.
segment BC. And another congruency, yes, Marilyn.
Segment AD is congruent to segment
All right. So these little symbols are conveying a certain language.
Yes.
And that's what makes mathematics a shorthand language. We say algebra is the shorthand of mathematics. We used to have shorthand, no? They had different symbols. But now we use shorthand when you say in your text, time. I have no time, T-Y-M. Right. Is it not? Okay. You say, can you? You say, C-N-U. So now we are inventing a different language. But language is so important in mathematics. Because all the rules that you are going to take care of or to memorize have to be done in symbols. Otherwise, it will be so lengthy, too wordy, too verbose, right? Now, let's see. We now go to another set. Maybe these are in statistics, but they're still in mathematics. What is that symbol? You haven't gone that far yet. It's sigma. It is standard deviation for a population. And then, if I have this, simple standard deviation for a sample. And then this,
The radius.
radius. Oh, I haven't taken up statistics maybe. That's why. This is for correlation. So now we're saying the symbols change meanings depending on the context. Like R could be your radius. But if you're taking statistics, R could be a correlation coefficient. You see? So there you are. How about rho? This is a Greek letter. Rho. Spearman rho. And which is also for correlation. How about this? What does it mean? Sum of. If I have that symbol and I say this, okay? Okay, sum of n. N divide, where n goes from 0 to 5. That means a lot, okay?
Yes.
So, what does it mean? When n is 0, cannot be that. But if I have this, it means something else.
Yes.
All right. So this means, in a long sentence, it means 1
1 over 2 raised to 0.
plus
1 over 2 raised to 1.
plus
1 over 2 raised to 2.
and
1 over 2 raised to 3.
and
1 raised over 2 raised to 4.
and.
Plus 1 over 2 raised to 5.
So now you look at it. It's such a big space user, but here it means something. Right? And so we add this. What is 1 over 2 to the 0?
1.
1. So this is 1, plus the next one,
1 half.
plus the next one,
1/4.
okay, plus the next,
1/8.
and the next,
1/6.
and the next.
1/32.
All right, 132. Otherwise, it's not 132, it's 1/32, right? You don't say 31, 32. That's straight reading. But you follow the ordinal way. You say 1, all right, 31st, 1/32nd, 1/35th. Okay? So it is a language, and that's the reason why we are here. Incidentally, what is the sum of these? This is by itself a language. It tells you what operation to do, right? Can you add this? Right. Sometimes we don't need to add. We can simply say, this is 1, then I have another 1, and I want 1/2. Okay? And I have 1/4. Right. And I have, what's the next? 1/8. And I have the next 1/16. And what is the next? 1/32. Aha. So what's the sum of all of these?
approaching to
It's approaching,
Approaching.
right? So the limit of this is going to be 2.
2.
Can I continue maybe? How much? 1/64. And I continue.
1/120.
Right. But somehow there's always some little thing that is left over. Right? But it approaches. So the limit of this is
2.
1 plus 1. The limit will be
2.
as x approaches infinity, it approaches 2. Okay? Now, that's a whole mouthful, right? And this is where we lose our students. Who cares about the limit? But if you draw it like this, it's smaller and smaller left over, then you say it's approaching a limit. You get it? So, is it a language?
Yes.
It's a language. And that's where we lose our students because the teacher will right away go and write limit without illustrating it. Okay? So now, let's see if we can get a few more examples. I have this illustration, right? What do you think these figures have in common?
height.
The heights.
The height.
They have the same height. You agree?
Yes.
And I showed you the source. The source is this. So they come from all the sheets. But what varies? What differs? The width, right? This is very wide, slightly wide, little less wide, narrow, narrower, narrowest. So you see, math is a language. You have to use language to compare. Now, on the other hand, if I say, for example, I call this X, and I call this A, B, C, D, E, F. What will be the sum of all the things if I collapse this? This is A, B, C, D, E, F. What will be the operation in language form? So, yes,
It's a
Summation.
yes. What is it? I say this is A, B, C, D, E, F. So it becomes like this. Put them together.
A plus B plus C plus D plus E.
All right. Then we go beyond already. A, B, C, D, E, F. All right. So there's one more. All right. And they have a common height.
Yes.
Not. So if I want the area of the whole thing that is collapsed, then it will be this. Right? Or if I don't want X, because X rubs me the wrong way, supposing I have H, then what will be the area of this? HA
Plus HG plus HC plus HE plus HE plus HF.
Okay? So what do you call that property?
Distributive property.
Very good. So you distribute the operation, right? Now, it's distributing the operation. Now, just suppose, do you think this together will add up to this? Which is bigger now? I want you to look carefully and observe. Which is wider, this put together or this one? Right? So you see, math is not just giving the right answers. It's really challenging you to use your estimation. right? Do you think they will add up to something more than this, less than this, or equal to this?
Equal.
Equal? Let's see.
Most probably.
I am now using the Dangkal method. Yes, right? Equal. All right? So therefore, can I now say that H, right, B plus C plus D plus E plus F is equal to H times what?
A.
Right. Now you have an equation. Right? It's an equation. And therefore, what is the ratio of this many things to this one? Since
1 is
one.
1.
1 is
to
to
one.
1. They are equal, right? So if you ask your brother, which do you want, these pieces of cake or one big piece? He might choose this because he thinks many pieces would be more. Right? So that's the illusion. But you can show that they are really equal. The small pieces are equal to the one big piece. That is language. Now, let's look at this. Would you say that these are congruent? They came from the same booklet, but would they have the same area? Yes. What kind of law tells you that they are equal? In other words, the area of this is equal to the area of that.
Yes.
Commutative.
Commutative.
Right? That there's no change in the area even when you change the position. But some teachers say commutative. Ano ba? Commuter ba? Right? The meaning of commutative, it just changes positions. So they're equal. Now let's see. I want to see from your visual judgment about how many of this will make this.
2.
If there are two of this that make this, how can I show? How can I state the relationship? Yes, this is equal to twice. So if this is A, this is B, state the relationship in the language of math.
A is equal to 2B.
2B. All right. How much? What fraction do you think this is compared to this?
1.
1/2. If this is 1, then how much is this? 1/2. If this is 4, how much is this?
2.
If this is 1/2, how much is this?
1
All
4.
right. If this is 2, how much is this?
4.
All right. If this is 4, how much is this?
1.
1. About how many of these are in here? About.
About 2.
Huh?
About 2.
About 2 of this make this. So what fraction is this compared to this?
1/2.
Half. About how many of this make this?
2.
2. Therefore, what fraction is this of this?
1/2.
What is 1/2 of 1/2 of a half?
1 4.
1/4. So what fraction is this compared to this?
1 4.
All right, now I have another ploy. I am going to look at this and I'm going to draw, right? Okay, right? So what fraction is this?
Still 1
It's 1/2. Would you agree that this is 1/2 of this one?
Yes.
About what part of it is this? Now, I want you to judge.
Less than 1/2.
Come again?
Less than 1/2 of this.
This is less than 1/2 of this.
Still 1.
Still 1/2.
Still a whole of that.
So now, what do you think?
Equal. They are equal.
Equal.
Oh, they're equal. How do you know they're equal? Show me. I tend to be a doubting Thomas. So, show me that they are equal. How would you do that? Okay, yes, Fritz, would you like to come to the board and show that they are equal, that the last two figures have an equal area?
Yes.
No, you need this? Or would you like to just touch the thing? Touch. Yes. So he saw the secret. Now, do you believe they're now equal? Yes. I just folded it over. By how much? At what point did I fold it over? At the halfway mark. So the height is half, but the base is still the same, right? So you say, you fold it over, that's the secret. And now it looks like that, and you get this, peel it over, and then put it here. Sometimes we can do proof. We call it demonstrative proof. In other words, what Fritz did is a demonstration proof, not proof by algorithms, not proof by theorems. It's just that. You see it, do you believe it? Yes, that's the important thing. Yes. So we have situations like that in math, but everything anchors on language, right? Let's see, for example, let's go over a particular knowledge that you have. If I say, for example, this is A, and this is A, and I complete that, what's the area? Pardon? It's A by A, right? Supposing this is B, this is B, what's the total area now?
A squared plus B
Square plus B squared. Supposing I say, I'll put this inside, not there. So what's the area originally?
A squared minus B squared.
It's A squared minus B squared. Supposing I have something similar, right? Pardon this. But the small one is here, right? What's the area of this before the cut? It's A and A. This is B, this is B. So now what's the area of the remaining?
A squared minus
It's
B
A
squared.
squared minus B squared, right? Now, if I have A squared minus B squared, remember your factoring?
Yes.
Yes.
What are the two factors of A squared minus B squared?
A plus B times A minus B.
A squared minus B squared is equal to A plus B times
A minus B.
You can memorize that even when you're half asleep. That's the easiest factoring, special product, right?
Yes.
Now, but I want it to be shown. Show me, right? Because you just got it from your teacher. How are you going to show me in a demonstration that A squared minus B squared is equal to that? There are many ways of doing it. Who would like to show it on the board? In other words, you're not just going to accept A squared minus B squared is equal to the product of A minus B times A plus B. We can memorize that. But I want the proof that it is the case, right? When I say A plus B times A minus B, what is the shape of that figure? Yes? What's the shape of two factors like this? This is A times B. It's a rectangle. But this time, we're saying A minus B, A plus B. It's still a rectangle. You get it? It is a rectangle. How can I show that? Right? We will be satisfied with our